Hello guys, so unfortunately I missed the chocolate pudding because I was getting mic'd up, so I have to make it up. And we're here to present you the adventures which we had with Scylla for past months in the AdTech industry. And I guess we will explain something more about how we process data, how big is the data, and how do we handle it in real time. So let me introduce myself. My name is Luboš Koščo. Thanks, Greg. It was close enough. And I worked in Sizmek as a senior software engineer, and I'm in the real-time bidding side. It's called Service Infrastructure, and I previously used to work for Sun Microsystems and Oracle on the data center management and monitoring. And in my spare time, I work on the open grok source code search engine. And sometimes I play with the Android applications and hybrid applications on the phones. And
hello everyone, my name is Michal Senkýř. I am also a senior software engineer, and I have background in both real-time and batch data processing. I was previously employed at Seznam.cz, which is Czech-only alternative of Google in the selection of their services. I am also a strong proponent of Scylla, and recently a strong proponent of Scylla too.
okay, so I'm not sure how many of you heard about Sizmek. Okay, few have heard. And what about real-time bidding or DSP? Okay, some have not. Okay, so let me give you some background about the company. So we are basically the largest independent buy-side advertising platform. And what is our specialty is that we basically decide or we help the decision process on whether to show you an advertisement by AI. And the platform is available almost everywhere. It's like 70 countries and 20,000 advertisers and more than 3,000 agencies. And we are delivering billions of impressions per day. And before you get to an impression, you basically have to process the bid request, and I'll explain that later. And we are processing like hundreds of billions of them per day. Let's get to the agenda of the talk. So to be able to achieve like such speeds of the real-time processing, we will explain like what's going on there in the first thing. Then we'll explain how we model this data to be so performant, give you some information about the hardware that we use, and we also did some small improvement on top of Scylla that kind of enabled us to process like more requests with the proper latencies and get them served faster. Michal will also talk a little bit about Spark. I mean, the Spark is an obvious topic here, and there are some optimizations which we did. Let's start with the use case. I mentioned the word real-time bidding because not like many people know what is it about. I'm wondering where should I point to. I'll try to point there. Okay. So I'll do it very easy so everybody will try to understand. You are the user. You are sitting in front of your computer, and basically you open up a page, you start playing a video, or you're watching on your phone some applications, and at this time basically the publisher, be it a page or an application or some video, sends a request to something which is called the RTB exchange. And this exchange basically is providing auctions and sending these auctions to various companies that are in AdTech business, and they need to basically react back and say, okay, this is a good slot for us, and we will like provide the impression there. So what happens here is that the exchange sends usually some basic information about the user, and it awaits the answer. There is some SLA ongoing in here. It's, I think, roughly like 100 milliseconds, And from these 100 milliseconds, if you get rid of the network latency, you get to like 70. And within those 70 milliseconds, you have to decide if you want to buy this slot, if you want to bid it, or if you just go to the next one. From these 70 milliseconds, basically, it's very important that you like look up based on the ID that came from the exchange, who is like the target, to be able to target it or target him programmatically. And we are roughly time-wise on less than 40 milliseconds. So if we can do this part within 40 milliseconds, then we're golden. And once this is done, what is going on that the reply goes back to the exchange. Exchange says, okay, you are giving the best price, and you're able to show the advertisement to the user. And then there is something which is called an ad server or the DMP site, and this will show the advertisement to the user. So that's roughly what's going on. So I mentioned this user identification and the user profile. We basically, to be able to know what you did last weekend, we store this in a user profile, and we do get the information into the user profile from multiple sources. We merge them, and we are trying to track like all the active devices and users, and we are going even above that. We are even able to track like the whole household, and you can imagine that these parts can be very, like you can have a lot of them, and they should be like very quickly connected and merged together. So that's why I mentioned this 40 millisecond. And because you have to put all of these requests into the 40 milliseconds, you're really down to a very short SLA. So it can be maybe even less than 10 milliseconds. And the user information, it gets queried for every bid request. Because if for example, you or the user did something 10 minutes ago, you want to have the latest information, and that's why like we are requerying it over and over again. There is some caching involved, but let's talk about it later. And after we have this information, then we are leveraging either restrictions or the AI models to help us decide whether to bid or not. So talking volume, we currently have around, it kind of moves because we have like a certain TTL where we keep the users, and we want to stay, or we want to have the users to be fresh, so we don't really keep old users. And this number right now is around 50 billion profiles. And I already mentioned that one single request can initiate multiple profile lookups, and the tens of millisecond latency has to apply for every one of them, so they together like be under the 40 milliseconds. The whole architecture is like distributed, so we have multiple DCs around the globe. We basically need to be very close to the bidding site, so this information gets to the bidder on time. How this user profile is modeled, I will reach over to Michal, and Michal will explain you more.
Okay, so let's get started on the data model that we chose. So as Luboš already said, there are these user profiles, and every user profile consists of multiple different attributes. These attributes can be divided into two types. The first type is the primitive attribute, and the second type is the collection attribute. The primitive attribute is usually a single value, but this does not have to be true, because these values are complex structured values. Like we can have a primitive value that contains a list, but what is important for these attribute types is how we want to write them, what kind of semantics do we want to use when writing them. For the primitive attributes, there are override semantics. So when we are writing this kind of attribute, we want to override the previous value on the whole. So for example, when Luboš was talking about the household clustering, when our pipelines try to compute which profiles belong into a cluster, they write the whole list of the related user IDs into a primitive attribute, not into a collection attribute, because we don't need to add new profiles into that, but overwrite when we recompute the whole clustering. There are also operations that we want to support. There are two types of operations actually, lookups and mutations. For lookups, the simplest type of lookup is the single profile lookup. This works just like you would expect. We get a user ID and we want to get all the attributes or a selection, a subset of the attributes for that specific profile. The second case is actually a little more complex. That's the profile cluster lookup. We want to look up the main profile. From that main profile, we want to get the attribute which says which are the related profile IDs, and then we want to look up all those profiles and merge them into the main profile as they provide supplementary information. Like this, each profile can reference other profiles. There's sort of a graph, and we do merging usually on the collection attributes. Sometimes we want to also do some sort of complex logic when operating on primitive attributes. And then there are mutations. We want to support three types of mutations. The first one is profile merging. That's essentially the right semantics that I was talking about earlier. Given a structure of the profile or like the representation of the profile, we want to write that into the database. For primitive values, we want to override. For collection attributes, we want to append. There are also two types of deletions that we want to support. Attribute deletion, where we remove the whole attribute, like all the values, for example, for the collection or the whole primitive attribute. This is useful when we want to just delete the profile or something like that. And then there is value deletion, where for collection attributes, we want to delete specific values from that collection. So we we want to specify the literal values that we want to be removed, and we use that for deletion. Then there are also housekeeping processes that we want to have in our system. The first one is TTL enforcement. We couldn't use the TTLs that are in Scylla because we need more complex processing for TTLs. We don't only have TTLs for each attribute, but we also want to enforce a TTL for whole profiles. And we want to, for example, enforce a longer TTL for a profile that is more active. And we want to delete so-called one-hit wonders as soon as possible. So for that, we needed to create a special Spark job. Another process is collection attribute pruning. Because collection attributes have the append semantics, you could argue that when we are writing new and new values, the collection attribute just gets bigger and bigger. So we needed some sort of a process that would go through all the profiles that we have in the in the database and do some sort of pruning. The simplest case is to keep only n newest elements, but we also needed to do some sort of complex processing for some of them, like deduplication of values that are keyed for in some way.
So wait a second, Michal, and then when do we run them, the housekeeping jobs?
We run them off peak because we don't want to affect
okay.
latencies during peak hours.
And you mentioned that we are doing the collection attribute pruning because of the disk space?
We want to do the collection attribute pruning because of disk space, but also we found out that there is an effect on latency. As the collection attributes or the values get bigger and bigger, the latency gets worse and worse. So we are doing this housekeeping processing during off-peak in order to reduce latencies during peak. So in the end, we created this sort of data model, or we chose this sort of data model. There are two tables. The first table is for primitive attributes. It has the partitioning key of the user ID. As you would expect, for each attribute, there is a separate column that houses that primitive value. For collection attributes, there is a separate table which has also the partitioning key as the user ID, but there are also two columns, the attribute ID and the value, which make up the clustering key. So for different values, we can have multiple, or for different elements of the collection, we can have multiple rows, choosing the clustering key like this allows us to have multiple values for that specific partition key. There are multiple benefits for this data model. The first one is co-partitioning. These two tables have the same partitioning key, so this means that when we are fetching a single profile, all of the attributes of that single profile will be housed on the same shard set, will have the same replicas. This is not as helpful when doing lookups, or we can't use that really when doing lookups, but when we are doing full scans and we want to create an RDD in Spark for the profiles, we can use that for our advantage, and I will explain later how. There is also grouping by the collection attribute. So we have efficient lookup by an attribute ID for the collection attributes. As all the values are sorted according to the clustering key, the attribute ID and the value, that sorting enforces all values for specific attributes to be bunched together, and when Scylla is fetching that, it is more efficient. And there is also efficient value serialization. You can notice that all the values that are stored are blobs, actually. That's because we opted to use Google Protocol buffers to store those complex values for the specific attributes. This gives us more efficiency in serialization. It takes less storage space.
Michal, I'm not sure if it's a good time, but I spoke to some guys and they asked me, or they actually told me that Scylla has a collection type. And why didn't we use it? I mean, like...
Yeah, there is a collection type, but that type is actually optimized for smaller collections. There is actually even a limit of about 64,000 elements per collection, I think. So in order to not hit that limit, and in order to have more control over all those values, we did not choose that collection.
Okay, so they were trying hard to persuade me, but we did the right thing. Okay, great, thank you.
Okay.
Yeah, I guess I can tell you something about our server and driver configuration. So to accommodate all this data and all this computing power, we basically went on with the Scylla Enterprise 2018 1.5. Repairs automated thanks to Scylla Manager, so thanks guys. And the design of the cluster is that basically we have 7 data centers around the whole world, like I think 4 in EMEA, 2 in EMEA, 4 in US, and 1 in the Asia region. And basically we built a global cluster out of them, and the data centers are in each region. And we had to go a little bit smart on the replication purposes. So we decided to have a key space per region. So we only keep the data relevant to the region inside the region. We don't want to replicate all of them, but only some of them. So we had to go with such a hybrid solution there. And even though AL said that we shouldn't collocate the resources, we decided to divide hardware resources between Spark and Scylla. So the Scylla cluster will eventually, or will run the Spark jobs itself. And thanks to Glauber, I don't see him here, but thank you, Glauber, we, hey, we did some tuning to the, like, we're really read-oriented, so like 90% of the stuff is reads, and there are like 10% of the writes. So we basically did the background of the write jobs or of the write tasks, and these are the changes to ScyllaYAML, which differ from the default setting which you get when you install Scylla. With the Java, okay, I forgot to mention that we're mostly like a Java shop. We have some stuff in Scala as well because of Spark, and we went with the custom driver that Glauber already mentioned. So we are using the SharDever driver. We've been like testing it, and it works. You've heard this for past 2 days, almost on every session, so I'll just repeat that. So we increased the connection to match our number of CPUs, and I mentioned this hybrid replication. So basically we leverage the Scylla replication in terms of data centers, and for some of the attributes that Michal explained, we don't need them replicated in all of the data centers. So some of the attributes are only written to the local region key space and not to the other key spaces. So I don't know if I can give an example. So if there's some data like behavioral tracking, like I want to see what the user did, I obviously don't need to have it in like Europe because the user is based in US. So we basically write this data only to US, and we don't replicate it to the other key spaces which are in Europe or in Asia. We had to develop our custom retry policy, but it's basically extending the default ones. And to keep the data size small, we are working with LZ for compression, and it works well. We had to do something more on top of Scylla, or actually, it's a tricky. We leveraged Scylla to give us more performance on top of Scylla, and we created a short-lived caching table and solution, and I'll let Michal explain you the internals.
Okay, so when I explained what kind of operations we needed, there was that one lookup operation for the profile cluster. In the simplest possible case, without any caching, What this does is it looks up the main profile, then reads the related user IDs, and then it looks up all the profiles for those user IDs and does some sort of merging. So this increases number of read requests for Scylla significantly. So for the related profiles, as they only provide supplementary information, we could do a sort of caching because they're not as time sensitive, and minor staleness in there is or was acceptable. So we created a new table. Oh yeah, that's the concept of the caching. So we are getting the main profile and the cached combined profile from Scylla. And if that combined profile does not exist, we do a lookup of all the profiles, the related profiles. We merge them together and write that combined profile into the cache. So for that cache, we are actually writing, as you can see here, we are actually writing the combined profile, the merged profile, and we keep that in a separate table with its own key space. That key space we could consider, or we considered how to define replication for that key space. The first most obvious solution was to have the same replication for that key space as for the profile key spaces. That would increase load on Scylla because there has to be some sort of replication, but we would keep that co-partitioning benefit. However, as co-partitioning is only good for us when scanning the full table of profiles and creating all the profiles, we don't want to use a cache for that. So it would not give us any benefit. So we opted for disabling replication for that new key space, which lowered the load on Scylla because there does not have to be any replication. A side effect of that is that token range replica locations are different, so we had to contact potentially different nodes when looking up some sort of a profile, but that was okay because we would only use that for profile lookups. So for this new key space, we wanted to have it as much in memory as possible. So we needed to minimize the disk usage. So we selected time window compaction strategy for this new table in that new key space. Even though we do not use it's not, the data is not really time series data, but for the purposes of compaction, it has the benefit of being ordered by the time to enforce the TTL more easily. So the compaction window we set to the TTL. In our recent case, it's 10 minutes. The minimal threshold for the compaction strategy we set to 2, so as to force the compaction or influence the compaction to compact SS tables as soon as possible, as soon as they are created. There are 2 SS tables in the final configuration. One of them is actively read because that's the SS table that has been recently flushed, and there can be records where TTL has not yet been passed, and the other SS table is kept there for compaction purposes. When we did some measurements on the cache efficiency, we found out from some statistics on the vid requests that returning users made up more than 60% of users that we encountered during the TTL period of 10 minutes. But actually, the cache hit ratio was even higher because we encounter a user more than twice usually. So the number of bit requests for a multiple occurrence user is actually higher than 2. So the next thing is Spark interoperability. That's how we, or I will try to explain how we used Spark for the housekeeping processes that I talked about earlier. So every one of you probably knows that there is some sort of Cassandra connector provided by DataStax. Spark Cassandra connector, that's an RDD implementation actually. It has a few useful features. One is shared database sessions. So when a session is being opened for a particular Spark partition to be processed, it gets kept open for other Spark partitions that are being processed on that same node, which is beneficial. It also has a token range partitioning, which gives limited shard awareness because token ranges correspond to shards as or shard sets because there is no token range that goes on multiple shard sets. So reading an RDD through the Cassandra connector is actually shard aware, but writing such an RDD is not shard aware, as there is some sort of batching, but when doing this sort of batch, it can either be per partition or it can be per node set or replica set. And that is based on hosts. So that was a feature that we lacked. There is also location awareness that comes into play because we opted for co-location of our Spark cluster and our Scylla cluster. So when you are running the Spark cluster on the same nodes, the Spark RDD is actually created in such a way to minimize traffic between nodes. But in the end, we created our own custom RDD implementation. In order to, or the greatest consideration or the greatest reason to do this was to take advantage of our co-partition tables, because we needed some sort of joining between the primitive attribute table and the collection attribute table. When using Spark Cassandra connector, we would have to load the data for the primitive attribute table, load the data for the collection attribute table, and then do a Spark join, which would create shuffle files and consume disk space, and we wouldn't even know if it would not require more resources than are available to us. So we did this sort of joining when creating the actual RDD. So when we are processing or creating a partition for that RDD, we are doing 2 queries, one for one table and one for the other table, and doing a join immediately after we load the data. We also have aggressive batching. We accumulate unlocked batches, but per shard set, as we are using the new Cassandra driver or Scylla driver. And that enables us to load or to read which shards that data is on or would go to. We have special logic for flushing for this batching. We have size-based flushing and time-based flushing and so on. So we could do our own thing. And we also have a new operation for element deletion semantics. So in order to delete specific elements in the collections, we just had to create an RDD of the stuff that we wanted to delete and could run that new operation on that, and we would get that element, that collection how we want it. That's useful for that collection pruning. We also created a new implementation of the DataFrame data source in order to work with our protocol buffers. We defined conversions from the protocol buffers to the Spark or the catalyst types. This gave us advantage using we could use this catalyst query optimizer in order to optimize the queries that we sent to Scylla, or that Spark SQL processes, and we also added what's it called? Predicate pushdown. Predicate pushdown. That's filtering on columns that the Spark SQL query has to fetch from Scylla. So we wouldn't unnecessarily fetch more data than we needed. We also got tungsten serialization, which is optimized for Spark operations, and we also got HiveQL support. So we could do things like counting percentiles and other more complex stuff. Lubash?
I want to kind of point out one of the optimizations which we did, and it was there throughout the whole talk. We basically are using this Java driver, and this one which comes from Scylla. And I'll give you a number, but this number is kind of, take me easy. It's number based on our normalized profiles. So I think in real time, it might be slightly less effective. But because of these shards, we had the same data with the old driver. We used the new driver, and we got around 28% increase in throughput just by switching the drivers to be shard aware, to get rid of the coordinator stuff that Glauber explained on his talks. So, and with that, I'd like to give you a conclusion. I didn't mention, or we didn't mention, what's the database that we are replacing. Our old user profile store was running on HBase, and this comparison is based HBase versus Scylla. And we were able to get down really from 77 HBase nodes to only 16 Scylla nodes, and the same affected like the cores and the RAM in there. And I'll let Michal to elaborate a little bit on the disk, because that's the funny part. That's what you are interested about. So I think
Yeah.
we can.
Yeah, for the disk, actually, we got more requirement for the disk space because of the new data model. Previously, in our HBase implementation, we used dynamic column creation. We could create new columns, so we stored a collection into some base column, and then added new columns as we added to that collection. So we had sort of append collections, and then there was a job that merged all of that together and wrote that into the base column for that collection. In Scylla, actually, in the new data model, it is much easier to work with the individual elements, as we did not have to, we do not have to work with those collections, those protobuffer collections.
Yes, Scylla basically helped there, so we sacrificed disk space for the convenience of working with the data within Scylla.
Yeah. And we also got high availability. Because HBase, when a node goes down, another has to be elected to replace that node. For Scylla, all replicas are the same. One thing we had to consider was eventual consistency. Because for HBase, we got strict consistency, for Scylla, eventual consistency, but at the end, we decided that eventual consistency is fine for us. So make sure to consider that when migrating from a different database, not from Cassandra, obviously, but from something else in the CAS diagram.
The mileage basically can differ. I mean, like, it can be slightly more challenge when migrating from HBase than from Cassandra. Okay, thank you very much, guys.